Right. So we've just worked an example. Let you go back and watch that if you haven't already seen it. We're going to continue on with lecture 9 here. Now, in lecture 8, we simplified and defined first law for closed stationary systems. So two adjectives being applied to this word systems here, closed and stationary. Closed and stationary. Uh, well, if it's closed, that means the only way energy is going to come into or out of the system is going to be heat and work. So I'm going to add the heat in, subtract the heat out, add the work in, subtract the work out. If it's stationary, the only type of energy that can change is going to be the internal energy. In minus out equals change. So add your in, subtract your out, set that equal to your change. Now, we introduced this concept last time about the process of writing a first law equation, right? Process is a step-by-step process of writing out a first law equation. Step 1, draw your system. And then step 2 is think about what energies are crossing the boundary and draw those. And then step 3 is use those, whatever energies you've drawn in step 2 to create the left-hand side of your equation. You don't have to write out all 4 of these terms. Only write out the terms that have either something coming in or something going out. That's your left-hand side. Your right-hand side, then, if it's a stationary system, is just going to be M delta U, the internal energy change, which I'll need most likely other properties to try to find those, right? And that brings us here. I always say that there's a few ways that you can find internal energy changes. The first one here is just simply tables, right? Good for us in our textbook, that is water and refrigerant 134A, R134A. I need 2 properties in order to use those tables, at least 2 properties. Normally, 2 properties is enough. We spent all of chapter 3 talking about that. We're in chapter 4 now. We're going to continue to build on what we learned from chapter 3. The second way I can determine U values is the first law. All right, the first law. Notice this equation here, right? There's U values right there. This is an equation. So as long as everything else in this equation is known or can be considered 0, then I can use this to solve for an unknown U value. I can only solve for one, or I can also solve for a change in U values, but I can use the first law itself to solve for an unknown U value. That is a possibility that's on the table. The third way is a new concept to us. You've had chemistry before you've taken this class, so it shouldn't be, well, it's new to us, but we're going to look at specific heats. Right, so let's consider specific heats then. And how do we use those? Well, first, let's figure out what is a specific heat. Again, in a chemistry class, you probably saw this, but a specific heat, by definition, according to the Chengel and Bowles Engineering Thermodynamics textbook, that is the energy required to raise the temperature of a unit of mass of a substance by 1 degree. It's dependent on the substance being heated. Water, for example, liquid water has a very, very high specific heat content, especially compared to most other substances that are plentiful and especially non-toxic. Also is very dependent on the phase. What do I mean by that? Steam, water vapor, is about half the specific heat content, about half the energy density of liquid water. So liquid water is like 4.2 kilojoules per kilogram Kelvin to raise its temperature by 1 degree Celsius or Kelvin. Steam in the vapor form, water in the vapor form is about two-ish kilojoules per kilogram Kelvin. So about a little less than half in the vapor phase is the specific heat. So the phase is going to determine the specific heat. Temperature will influence it some slightly. It's not a huge influence. We'll track that as we move along. Okay. Now, in a chemistry class, if I were teaching a basic chemistry class, and normally in like Chem 1, Chem 2, I'm dealing with a lot of people in there that are allergic to math and calculus what? We really are going to have to, if I'm teaching one of those classes, I'm going to have to oversimplify the math. Um, and a way we oversimplify that is we say, well, C sub P is for constant pressure. And, oh, should have closed my teams out. C sub P is for constant pressure, and C sub V is for constant volume. And those just don't work for us. Just not at all. They just go away. That's what the P and the V stand for, yes, but that's not what we're going to use them for. C sub P for us is going to relate H's, enthalpy values. And C sub V we're going to use to relate U values. U's. That's what we're after here. Okay. So with that in mind, let's see what I mean here. Why is that? Well, if I did hypothetically have a process where I have constant pressure, so some sort of a weighted piston cylinder, I apply a constant force spread out over an area, generate a constant pressure change in this piston. So if I heat this substance, whatever's in this piston up with some sort of a heat source, terribly drawn flames there, right? Pouring Q into this piston. And if the piston is allowed to hold constant pressure, that means that the volume is going to change. And so if the volume changes, that means there's boundary work. So if I'm adding heat to this piston over here, right? If I'm adding heat to this piston and he's changing volume. Well, that volume change causes boundary work, or boundary work, the system must do boundary work to the surroundings in order to expand. That boundary work means additional energy is leaving this piston. So that means I've got to add additional heat to overcome this boundary work. I'm adding additional heat to overcome this boundary work in order to get the same volume change by the amount of heat I'm adding. So what that means is because of this, C sub P is going to be greater than C sub V because C sub P is going to account for this boundary work term. C sub P accounts for this boundary work term plus the heat in order to cause the same temperature change. Okay? All right, and I know that's not necessarily obvious, but that's part of hopefully that helps you remember it. See, the simplest takeaway here is C sub P is always larger than C sub V. The reason for that is it has to account for the boundary work as well. All right, and I see that I've got, yeah. So I've stolen my own thunder. Work goes from the system to the surroundings. Additional energy is required to increase the temperature. So C sub P is larger than C sub V. Okay. Now, we've discussed before the idea of inexact differentials, right? And partials. So we've seen the inexact differential, we've seen the partial differential, and we've seen the ordinary differential before. Um, You'll see these in your text from time to time. The inexact is when we're dealing with potentially more than one variable. The partial is when you're dealing with more than just one variable. And the ordinary or the regular differential is when we're just dealing with one variable. So that's what the partials are telling us here. What are we saying, though? If we look at the idea of specific heat, C sub V times a change in temperature yields to us a change in energy, right? Specific heat, by definition, we said earlier, that's the amount of energy required to raise the temperature of a substance by a certain amount, right? So it's specific heat represents the energy divided by the temperature, energy per unit temperature, essentially. And that's what we're saying here is C sub V allows us to relate the change in internal energy to a change in temperature. And C sub P allows us to relate a change in the enthalpy to a change in temperature for most substances. We'll see it. Um, Anyway, we'll move on from there. Okay. Now, we're using partials here. If you're looking on the text, they'll use partials initially to describe how these properties relate to each other. The U value might be dependent on more than just temperature. We see that with the water in our 134 tables, how both pressure and volume also have some impacts here, where they fall on the PVT surface. Same thing with enthalpy. So we're using partials here because we know there's more than one variable at play, but there are situations that we can encounter where H and U are functions of temperature only. And so we know for ideal gases, U and H are functions of temperature only. How do we know this? Scientists and researchers have done this for years. They've looked at this very carefully. They are very comfortable that temperature is the driving factor for something that's behaving as an ideal gas. Now, nothing truly behaves as an ideal gas, but it's a really nice estimate for things that are in the gaseous phase. Terrible estimate for liquids, not a great estimate for vapors, but for gases, for us, that's air, carbon dioxide, hydrogen, things that are normally in the gaseous form, it's a fair estimate. The internal energy and enthalpy of these substances is going to be a function of temperature and temperature alone. Therefore, no partials needed like what we see here in the previous slide. We can use regular ordinary differentials, regular D's here, to describe this change. So what we're saying is that if I say that a change in temperature, dt, times the specific heat, C sub V, gives me a change in U. And here we're talking about an infinitesimally small change. An infinitesimally small change in temperature times the specific heat is equal to an infinitesimally small change in internal energy. Well, if I integrate both sides of this equation then, integrating both sides of this equation, well, now I've got the integral of C sub V dt is equal to the integral of du. Well, the integral of du is just u. I'm going from state 1 to 2 on both sides of this equation here. So the integral of du from 1 to 2 just becomes u2 minus u1, delta u. And then we can do the same thing with C sub p. If I take C sub p and integrate it across a temperature change from state 1 to 2, that's going to give me the integral of dH from 1 to 2, which is just h2 minus h1. So nice. So, okay, well, I'm saying that I can find delta U, which is a term that goes back into my first law equation right here, right? Delta U, if I can figure out how to integrate C sub V with respect to temperature, this works. So what does that mean? That means I need to know how C sub P and C sub V vary as functions of temperature. Okay, well, so with that in mind, if I were to go look at table A2 part B, table A2 part B, that's in the back of your book. I don't know what it is in the 10th edition. Here in the 6th edition, it's page 912. Now notice table A2A has ideal gases at specifically 300 Kelvin. That's room temperature. Now, how often are we dealing with temperatures at room temperature? Very rarely. In fact, it's very rare we use this table. If you're using this table, until you get to like chapter 10, you're probably doing it wrong. Don't use this table unless you just have to. Use this table. This is the table we're going to use for the most part. Table A2B. A2B, that's at various temperatures. So I've got ideal gas properties at various temperature. I've got here C sub P and C sub V, now at varying as a function of temperature. And the question on our slides here is how much change realistically can you see between C sub P and C sub V as the temperature changes? So if we go look at that, notice that at just about any temperature, C sub P for air is 1, and C sub V for air is anywhere from 0.7 up to about 0.8, up to about 1,000 kelvins, right? So a really high temperature is when it just starts getting above a significant change. So what we're saying here is if I'm going from like 400 Kelvin up to 700 Kelvin, notice how much it changes. We're going from like 1 down here to 1, or zero point 0.7 down to maybe 0.8, and somewhere, so in between about 0.75. Right? And that's kind of the idea is for most applications, we can easily assume a constant specific heat somewhere within our operating range. And what we're going to do is we're going to say this is going to be at the average temperature. We're going to find the specific heat at the average temperature, and we're going to assume that it's constant. Now, if you really like, there is this table here. Our best models for the specific heat is typically a third order polynomial. And so you can go find your substance in here and go find these, find the coefficients according to this model here, and then plug that into this equation back here. I can integrate then C sub P to give me delta H based off of this model equation. Right? And you're more than welcome to do that. I'm not going to stop you from doing it. I'm not going to do it. I'm not going to do that. I'm going to do this one. I'm going to assume constant specific heat at my average temperature, and I'm going to use that as a good approximation. Here's where we're going to pick up the next video.